Hello students, welcome to this review lecture 2. In this lecture, we will briefly review the signal estimation by optimal linear filters. We discussed optimal linear filters, then adaptive implementation, adaptive filters and Kalman filters. We will briefly discuss those. Winner filter assumes a linear filter structure for the estimator and estimates the filter coefficients by applying the minimum mean square error principle. So, winner filter always assumes a linear filter structure. This is Xn is the signal, Vn is some additive white noise, Yn is the observed signal. It is passed through this linear filter, we get the estimated signal. This estimated signal should be optimum under the minimum mean square error criterion with this linear filter structure. Given random observations yn minus m plus 1, yn minus m plus 2 up to yn and then to yn plus n. So, we have a block of signal from time instant n minus m plus 1 to n plus n, capital N. So, for this duration signal is available. Our minimization problem will be now minimize E of xn minus this filter output, that is summation hi into yn minus I, yn is the input signal, I going from minus n to m minus 1 whole square. This we have to minimize over hj, j going from minus n to m minus 1. And we derive the Wiener-Hoff equation corresponding to this. If we differentiate with respect to h of hj, h of hj, we get the Wiener-Hoff equation given by Rxy of j is equal to summation hi into Ry j minus I going from minus n to m minus 1. We discussed the FIR Wiener filter, FIR Wiener filter. Here we have to minimize. Filter is x at n is equal to summation hi into yn minus I going from 0 to m minus 1. This is the MTEP FIR filter we considered, and the filter parameters were obtained by applying the orthogonality principle. What was that? E of signal minus the filtered output, that is hi into yn minus I going from 0 to m minus 1. So, this is the error. This error is orthogonal to data. So, y of n minus j, that is equal to 0. So, from this is the orthogonality condition. From this we will get that Rx y of j is equal to summation hi into Ry of j minus I going from 0 to m minus 1. So, Rx of j is equal to summation hi into Ry of j minus I going from 0 to m minus 1. That is true for j is equal to 0, 1 up to m minus 1, because these are our data points. So, that way this Wiener-Hoff equations we derive for FIR filter, and similarly minimum mean square error also we can find out. MMSE minimum mean square error, that is given by E of E square n, and this is same as E of xn minus summation hi yn minus I going from 0 to m minus 1. This is the error into x of n. So, because remaining data are orthogonal to this error. So, that way we got it as Rx of 0 minus summation Hi into Ry of I going from 0 to m minus 1. So, this is the minimum mean square error. We also considered the non-causal IIR Wiener filter. In that case, impulse response sequence is infinite. Therefore, our x at n is equal to summation Hi into yn minus I going from minus infinity to plus infinity. So, in this case, the mean square error will be E of xn minus summation Hi into yn minus I going from minus infinity to plus infinity whole square. And this mean square error we have to minimize with respect to each Hj. Again, we apply the orthogonality principle. What is orthogonality principle? Error is orthogonal to data E of xn minus summation Hi into yn minus I going from minus infinity to plus infinity. This is the error is orthogonal to data y of n minus j going from minus infinity to plus infinity. So, this must be equal to 0. So, this is the orthogonality condition, and this orthogonality condition will give us, that is Rxy of j E of xn into yn minus j, that will be Rxy of j, that will be equal to this summation Hi into E of yn minus I into yn minus j, that will be Ry of j minus I. So, that way summation Hi into Ry of j minus I going from minus infinity to infinity, that will be equal to Rxy of j. This is the Wiener-Hoff equation which is obtained by applying the orthogonality principle. And here we have two sequences. Hi is known to be a two-sided sequence because impulse response is from minus infinity to plus infinity, and autocorrelation function is also a two-sided sequence. Therefore, we can perform convolution and then solve this problem in transform domain. So, non-causal IIR Wiener filter is therefore given by Hj convolved with Ryj is equal to Rxyj, j going from minus infinity to plus infinity. Then applying that transform, we will get, this is that H sequence, transfer function is Hz, here Syz is equal to Sxyz. So, from this we get that the transfer function of the non-causal IIR Wiener filter is given by Hz is equal to Sxyz divided by Syz plus power spectral density divided by the power spectral density of Y. And once we have Hz, we can apply inverse Z transform to find Hn. Now, how to find out the MSE? Again, same orthogonality principle we can apply, that is E of MSE is equal to E of En is xn minus summation Hi into yn minus I going from minus infinity to infinity into xn, because remaining part of the error will be orthogonal to this part. So, because remaining data part will be there, that part will be orthogonal to this error. Therefore, only this expression will come, and that is equal to Rx of 0 first term, and remaining term will be summation Hi into Rxy I going from minus infinity to infinity, that is Rx of 0 minus summation Hi Rxy cross correlation I going from minus infinity to plus infinity. Then we discuss causal IIR Wiener filter. In this case, the estimator x at n is given by x at n is equal to summation hi into y n minus I going from 0 to infinity. Because the filter is causal, this filter sequence is defined from I is equal to 0 to infinity. So, that way it is causal. And the mean square error is given by E of E square n, that is E of x n minus x hat n whole square, and this is to be minimized with respect to all h's. So, Wiener-Hopf equation again here is given by E of error is orthogonal to data, that is x n minus summation hi y n minus I going from 0 to infinity into error is orthogonal to data y of n minus j is equal to 0, 1 up to infinity. So, that way we will get first term will be r x y j and then remaining term will be summation I going from 0 to infinity into r y j minus I. So, if I take the difference between this and this, we will get j minus I. So, that way summation hi into r y j minus I going from 0 to infinity is equal to r x y j. So, this is the Wiener-Hopf equation corresponding to causal IIR Wiener filter. So, now you note that here is j is equal to 0 to infinity is a right sided or causal sequence, but r y is a two sided sequence. R y is a two sided sequence. Therefore, direct convolution is not possible. So, therefore, which cannot be solved directly in the transform domain. Now, we will apply the spectral factorization theorem to the power spectral density of y, that is S y z is equal to sigma v square into h c z into h c z inverse. So, that way we will use this relationship to get a whitening filter. So, that way apply the whitening filter h 1 z is equal to 1 by h c z to generate the innovation process. So, we apply, suppose this is my y n, pass it through 1 by h c z, that is the innovation filter or whitening filter to get the innovation sequence. Now, using this innovation sequence, x n now can be estimated using V n, and this was shown that the corresponding filter is given by h to z is equal to 1 by sigma v square into the causal part of s x y z divided by h c z inverse. This is the Wiener filter to estimate x n from the white noise sequence. And finally, we got the causal IIR Wiener filter as the cascade of this filter 1 by h c z and then into that h to z. So, V n is passed through h to n, this is V n. V n is passed through this h to z, that is the filter we have already obtained. Then we will get this estimator x at n. That way it is cascade of two filters, one is 1 by h c z and of course, this sigma v square is also there, 1 by sigma v square into. So, spectral factorization gives the whitening filter h 1 z is equal to 1 by h c z and this generates the innovation sequence Vn of variance sigma v square. And this innovation sequence is used to estimate x at n from Vn. So that way the transfer function of this filter H to Z, which is optimum, is given by this expression 1 by sigma v square into the causal part of Sxyz divided by Hc Z inverse. So this is the winner estimator of Xn from the Vn sequence. Now once we have this H to Z part, we can cascade it with 1 by Hcz to get the combined winner filter. Therefore, the winner filter will be cascade of this, and it is given by 1 by sigma v square Hcz into Sxyz divided by Hz inverse, and then we have to take the causal part. We considered one application, that is linear prediction of signals. The linear prediction problem was formulated as follows: y hat n is equal to summation hi into yn minus I going from 1 to m. So this is the linear prediction, or it is forward prediction problem. Again we apply the orthogonality condition, that is E of, here actual data is yn, and we are predicting y hat n, that is orthogonal. This is the error, is orthogonal to data. Data is y of n minus j, because it is m, j going from 1 to m, because we are using only past data up to n minus m. So that way from n minus 1 to n minus m. Therefore, this is the orthogonality relation we get, E of yn minus summation y hat n into yn minus j is equal to 0. Error is orthogonal to data, and from that we directly get the Wiener-Hoff equation or normal equation, and this is given by Ryj is equal to summation hi into Ryj minus I going from 1 to m, and this is, there are m equations corresponding to m values of j. And in matrix notation, this equation we write like this: this is the autocorrelation matrix into coefficient vector is equal to the autocorrelation vector. So this autocorrelation matrix, we see that it has very attractive property. It is symmetric and it is topless. For example, this sub diagonal will be same, this diagonal will be same, like that. This is a symmetric topless matrix into H vector is equal to Ry vector. And similarly, the mean square prediction error also can be obtained by applying the orthogonality principle, that is SPE. Minimum mean square prediction error is given by E of, that is error is yn minus summation hi into yn minus I going from 1 to m into yn, and the remaining part of error that will include yn minus 1, yn minus 2, etc. They are orthogonal to this error. Therefore, their contribution will become 0, and we get this only. Minimum mean square prediction error is equal to E of yn minus summation hi into yn minus I going from 1 to m into yn. So remaining term will contribute 0. So that way it will be equal to Ry0 minus summation hi into Ry of I going from 1 to m minus 1. So this is the expression for minimum mean square prediction error. Similarly, we also discussed the backward prediction problem. Here given yn minus 1 up to yn minus m plus 1, we predict y hat n minus m. So, y hat n minus m is summation bmi, this is the backward prediction coefficient, into y of n plus 1 minus I going from 1 to m. This is the backward prediction problem. And here also we apply the orthogonality again. Error is orthogonal to data, and that we apply. There are m data yn minus 1 up to yn minus 1 plus capital M. So, that way m data are there, and corresponding to that we will have this Wiener-Hopf equations. And from this Wiener-Hopf equation and linear prediction Wiener-Hopf equation or forward prediction Wiener-Hopf equation, we establish one important result, that is backward prediction coefficient at instant I is same as forward prediction coefficient Hm m plus 1 minus I. So, this is the relationship, and also we established that backward and forward minimum mean square prediction errors are equal. So, we use this result and also the symmetric Topliss structure of this matrix to derive the famous Levinson-Darwin algorithm that we have discussed in detail. We also discussed adaptive filter. The basic setup for the adaptive filter is like this. This is yn is the input, and this filter structure, generally it is an FIR filter structure, and this is the observed signal, and we get some output here that we call it as d hat n, and there is a reference signal in the case of adaptive filter. This is dn. We want to match the output of this filter with this dn. So, that way dn is the desired output which we know somehow, and we want to match the output of the adaptive filter with this dn, and whenever there is no matching, that error will be there. That error is fed back to update the adaptive algorithm, which will compute the filter coefficients adaptively. So, this adaptive filter coefficients will be computed by this adaptive algorithm based on this error en and the input signal yn, and then this updated filter will be used again to filter this yn and to get the estimate of the desired signal. The adaptation of the filter coefficients is based on the error en between the filter output and a reference signal dn, usually called the desired signal. Choosing dn is tricky, it depends on the specific application. For example, we showed how we can choose dn in the case of adaptive channel equalization and adaptive system identification. We considered one basic adaptive filter, what is known as LMS adaptive filter, and its updating rule was this: h of n plus 1 is equal to hn plus mu into en into yn. We get this by applying this steepest descent algorithm to minimize this cost function e square n. So, minimize e square n with respect to hi n, n is equal to 0, 1 up to m minus 1. So, this optimization problem, when we apply this steepest descent algorithm, we get this updating rule. So, this is the LMS updating rule. So, yn is the input and this is the FIR filter, and then d hat n is the output, and this is compared with the desired signal output. This is compared with the desired signal, and the error is fed back to the LMS algorithm. So, LMS algorithm updates the filter coefficient by this rule. It computes the error. Error is nothing but yn will be filtered at instant n with filter parameter of, so we will get d hat n, that is summation hi n into y n minus I going from 0 to m minus 1. So, we filter the signal yn with the filter coefficient at instant n, and then after that we will get the error. Error is equal to En is equal to dn minus d hat n. So, this error is used to update the filter coefficient h of n plus 1, that is obtained as that previous filter Hn plus mu into En into Yn. And we discussed several modification of this algorithm, that is NLMS algorithm, leaky LLMS algorithm, that is leaky LMS algorithm. Then for efficient implementation we consider block LMS algorithm and sign error LMS algorithm. The LMS is a very simple adaptive filter, but problem is how to choose this step length parameter mu. So, this depend on the eigen value of the autocorrelation matrix. Suppose we are filtering a WSS signal Yn, then the eigen values of the corresponding autocorrelation function of Yn will determine this filter step length parameter. So, that way we establish some relationship, that is mu should be lying between 0 and 2 by lambda max. This type of relationship we establish, and then also with the chosen mu, the LMS adaptive filter will not converge to actual winner filter. There will be always some excess error. That excess error will also depend on the parameter mu. And we also observed that the rate of convergence depends on the eigenvalue spread. If it is high, convergence rate will be low, and that was a serious problem in the case of LMS filter. And to overcome this, we considered the RLS adaptive filter. So, in the case of RLS adaptive filter, the error is sum square error. We discussed the least square estimation principle. Same principle is applied here also, and here the error to be minimized is sum square error weighted by a factor lambda to the power n minus k. So, that way the error to be minimized is epsilon n is equal to summation lambda to the power n minus k into square k, k going from 0 to n. So, from the beginning n is equal to 0 to current n, all the errors are considered, and this is given by summation lambda to the power n minus k into dk minus y transpose k into hn whole square, k going from 0 to n. And this is important that we are filtering all the past signal values with respect to hn, current estimate of the filter, and that way we are determining the error, and these errors are weighted by the what is known as the forgetting factor lambda to the power n minus k, and this lambda lies between 0 and 1. In the case of WSS signal, we can take lambda is equal to 1, and this is used to take care of non-stationarity of the data. So, for example, since lambda is a fraction as n tends to infinity, so lambda to the power n minus k, for k is equal to 0, it will become lambda to the power n. It will be close to 0 when n is large. So, therefore, for large value of n, it will give less and less weight to the previous errors. That is the idea behind tackling the non-stationarity of the data. Past errors are given less weight, present errors are given more weight. And that way we derive the RLS adaptive filter. We got a corresponding normal equation by filtering, that is del epsilon n into del Hn, that is equal to 0. So, from this we got a matrix normal form of normal equation, matrix form of normal equation, and which is solved by the matrix inversion lemma. We get a recursive estimator using the matrix inversion lemma. So, that way we discuss the RLS algorithm, and this RLS algorithm estimates the signal recursively. So, it is a recursive least square method. We discuss two forms of Kalman filter, that is scalar Kalman filter and vector Kalman filter. The scalar Kalman filter this uses the applies the model. What is the model? Model is AR1 signal. So, Xn is equal to A times x of n minus 1 plus Wn. So, Wn is a white noise, and A is a constant which is known, and A can be considered as a function of n, so that non-stationarity can be tackled. And observed data Yn is equal to Xn plus Vn. And we discussed that we derived using the innovation representation. That is, get the innovation. What was the innovation in Kalman filter? We got it as that is Yn prediction error minus summation Hi into Yn minus I going from 0 to n minus 1. So, this is the prediction error, and this prediction error we showed that this prediction error is an orthogonal sequence. That way we generated the innovation sequence. And we also considered the vector Kalman filter. It is a recursive state estimator and uses a state space model for the signal, that is Xn is equal to An into Xn minus 1 plus Wn. If we consider An to be time varying, then this state space model is Xn, that is the signal vector, is equal to An into x of n minus 1 plus Wn. Wn is a noise known as the process noise, and the observed data Yn is equal to Cn, a matrix. Cn is a matrix multiplied by Xn. Xn is the state vector plus Vn. Vn is again another noise vector, which is observation noise vector, which is uncorrelated with Wn and uncorrelated with Xn. So, that way Wn is assumed to be white noise vector, thus the covariance matrix QW is a diagonal matrix. Vn is also assumed to be a white noise vector with covariance matrix QV. Further, Vn is independent of Xn and Wn. The Kalman filter structure is given by this block diagram. So, yn, this is the input signal and this is the output signal, and normally we denote it by x hat n given n, estimation of the signal at instant n. And this is delayed by 1 unit. Here we will get x hat n minus 1 given n minus 1. And then if we multiply it by an matrix, we will get the predicted signal. So, this is the x hat n given n minus 1, this is the predicted signal. Now, to get the estimate, we use this predicted signal. In the observation equation, there is a multiplication of Cn and the state vector. Therefore, this predicted state vector is multiplied by Cn and we will get this predicted input vector. This is the predicted input. So, yn we are predicting here. This prediction will result error, that is the prediction error. This is the innovation. So, this is the innovation output. And this innovation output is scaled by the Kalman gain, and then this corrected value, this part is the correction term, and this correction term will be added to the predicted value. So, this x hat n given n minus 1 plus this value, that is k n n times y tilde n, that will be added and we will get x hat n given n. So, that way we see that here there is a prediction part and there is a correction part. That correction part is obtained by passing the predicted signal through that output matrix multiplier, and then we get the predicted input. That predicted input is subtracted from the input and we will get the innovation, and this innovation is used to get that correction term. This innovation is used to get the correction term. That way Kalman filter is a prediction corrector filter. I will conclude my lecture here, and this is the end of the course. I hope that this course gave you a background on statistical signal processing. There are advanced techniques of statistical signal processing which was not possible to cover in this course. Thank you.